March 9, 1942. The Fisher Body Plant in Grand Blanc, Michigan. The production floor stretched 3 city blocks in every direction, a maze of steel and shadow where the thunder of pneumatic hammers competed with the screaming whine of grinding wheels. Joseph Moretti stood at Station 17, watching a Sherman tank hull move past on its crawler track at a pace that made grown men want to weep. The hull should have been complete by now, ready for turret mounting. Instead, it sat half-finished, waiting for rivet teams to punch another 800 holes through quarter-inch armor plate. Each rivet required heating, positioning, hammering, and inspection. Each rivet took time they didn't have. In Moretti's work, apron sat a forbidden tool, an oxyacetylene cutting torch modified with an attachment that violated every Army Ordnance specification and safety protocol in the manual. What Moretti didn't know, what none of the 4,000 workers grinding through double shifts could have predicted, was that within weeks, his unauthorized modification would trigger a transformation so complete that American tank production would shift from an ambitious goal into an unstoppable industrial avalanche. The crisis had crystallized 6 months earlier on December 7, 1941, when Japanese aircraft turned Pearl Harbor into an inferno. Within hours, every production quota in American industry doubled, then doubled again. The War Department's demands seemed divorced from physical reality. 45,000 tanks, 60,000 tanks, build them faster, build them stronger, build them yesterday. The problem wasn't desire or determination. The problem was time itself. Traditional tank construction relied on riveting, a technique inherited from naval shipbuilding and railroad manufacturing. It was proven, reliable, and understood by every metal worker in America. It was also brutally, inexcusably slow. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Each rivet in a Sherman tank hull required multiple operations. First, workers drilled or punched holes through the armor plate, an operation that dulled bits rapidly and required constant tool changes. Then riveters heated the steel fasteners to cherry red in portable forges, a process that filled the factory with smoke and heat. Hot rivets were carried in tongs to the hull, positioned through aligned holes, and hammered flat before they cooled. Each rivet needed to be driven from both sides simultaneously, requiring coordinated teams working in cramped spaces inside and outside the hull. The Sherman M4 required approximately 1,900 rivets in its hull assembly alone, at 3 to 5 minutes per rivet, accounting for drilling, heating, positioning, and driving. The riveting process consumed nearly 160 hours of labor, and that was just the hull. The turret, sponsons, and internal structure required thousands more. In January 1942, American industry produced exactly 284 medium tanks. Germany's factories, even under Allied bombing, managed 400 per month. The arithmetic was savage. At current production rates, the United States couldn't replace losses fast enough to maintain offensive operations, let alone build the overwhelming force needed to liberate Europe. The Army Ordnance Department understood the crisis. Their solution was to build more factories. Chrysler's Detroit Arsenal broke ground in Warren, Michigan. Fisher Body converted automobile plants in Grand Blanc and other locations. The Pressed Steel Car Company in Pennsylvania began tool-up for tank production. Federal Machine and Welder took contracts. By spring 1942, 10 major facilities were ramping up for Sherman production. But building more factories didn't solve the fundamental problem. Each factory still used the same slow riveting process. You couldn't outrun time by multiplying it across more locations. The real answer required changing the process itself, and that change was already happening, quietly, unofficially, in direct violation of established specifications. Joseph Moretti had learned welding at the Brooklyn Navy Yard in 1938, working on destroyer hulls before the war. Welding was revolutionary in naval construction, replacing riveting with continuous joints that were stronger, lighter, and far faster to execute. A skilled welder could lay down a seam that would have required dozens of rivets in a fraction of the time. But welding carried risks that made conservative engineers nervous. Weld failures could be catastrophic. A poorly executed rivet might work loose or crack, but typically failed progressively, giving warning signs. A bad weld could fracture suddenly under stress with no advance indication. The heat of welding also warped metal in ways riveting didn't, potentially distorting critical dimensions. When Moretti transferred to Fisher Body's tank plant in January 1942, he found an industry locked into traditional methods. The specifications issued by Army Ordnance explicitly called for riveted construction. The reasoning was sound from a military perspective. Field repairs could be done with basic tools. Any mechanic could drill out damaged rivets and replace them. Welding required specialized equipment and trained operators, resources that might not be available in forward combat zones. But Moretti saw waste everywhere he looked. Riveting required holes, and holes were structural weaknesses even when filled. Each rivet point concentrated stress, creating potential crack initiation sites. The overlapping plates needed for riveting added weight without adding strength, and the endless time spent heating and hammering individual fasteners while tank hulls crawled through the factory at glacial pace. During lunch breaks, Moretti studied the hull assemblies with the eye of someone who'd welded battleship plates. The seams where armor sections joined were perfect candidates for continuous welding. Instead of 200 rivets along a join line, a single continuous weld could bond the plates in minutes rather than hours. The weld would be stronger than the rivets, eliminate the stress concentration points, and reduce overall weight. In February 1942, he approached his shift supervisor with calculations and sketches. The supervisor, a man named Dutch Hawkins who'd spent 20 years in automotive manufacturing, listened with skepticism that bordered on hostility. You want to change specifications that Army engineers spent months developing? You want to replace proven riveting with welding that might fail in combat? You want to take responsibility if a hull cracks under fire because some hotshot had a better idea? Moretti persisted. He offered to weld test sections on his own time. He brought in photographs from the Brooklyn Navy Yard showing destroyer hulls under construction, massive warships trusting their structural integrity to welded seams. He cited metallurgical studies on weld strength versus riveted joints. Hawkins remained unconvinced, but agreed to raise the issue with plant management. The response came back in writing 2 weeks later. Welding was not approved for structural hull assembly. Specifications would not be modified without explicit Army Ordnance authorization. Any unauthorized changes to construction methods would result in immediate termination and possible prosecution for sabotage. The letter was polite but absolute. The matter was closed. Except it wasn't closed for Joseph Moretti, and it wasn't closed for dozens of other welders scattered across American tank plants who saw the same inefficiency and reached the same conclusion. What happened next wasn't coordinated conspiracy. It was something more organic and ultimately more powerful. It was workers making practical decisions in the face of overwhelming urgency. Moretti started small. On night shifts, when supervision was lighter, he began welding non-structural joints that specifications didn't explicitly address. Internal brackets, secondary support members, places where welding saved time without obviously violating the structural requirements. Other welders noticed and began doing the same. The practice spread through informal networks, the way practical knowledge always moves through industrial workforces. By April 1942, Fisher Body's Grand Blanc plant was producing Sherman hulls significantly faster than projections suggested should be possible. On paper, the hulls were still riveted per specifications. In reality, perhaps 30% of the joints were now welded. The distinction mattered greatly to Army inspectors and production managers. It mattered not at all to the workers who'd quietly decided that winning the war was more important than following outdated specifications. The breakthrough came from an unexpected direction. In May 1942, a Sherman tank completed at Fisher Body was selected for destructive testing at the Army's Aberdeen Proving Ground in Maryland. Destructive testing meant exactly what it sounded like. Engineers would subject the hull to stresses far exceeding combat conditions, searching for failure points. They'd test armor penetration resistance. They'd measure structural integrity under explosive loads. They'd deliberately try to break the tank to understand its limits. The test hull happened to include several of Moretti's unauthorized welds. When Army engineers cut sections from the hull for metallurgical analysis, they discovered welded joints where specifications called for rivets. The discovery triggered immediate investigation. Fisher Body Management was contacted. Production records were examined. Workers were questioned. The expectation was scandal. Sabotage investigations. Production delays while the plant returned to proper specifications. Instead, something remarkable happened. The test data showed that the welded sections performed better than the riveted ones. Under stress testing, welded joints proved stronger and more fatigue-resistant. The hull sections with welded construction showed less deformation under load, and critically, the production time reduction was measurable and dramatic. Colonel James Fowler of Army Ordnance faced a decision that would have destroyed lesser bureaucrats. He had specifications that explicitly required riveting. He had a contractor that had violated those specifications, and he had test data proving the violations produced superior results. The conservative choice was obvious. Enforce the specifications, discipline the contractor, maintain control over the process. Instead, Fowler did something that revealed why some military officers rise above their peers. He asked a different question. Not, were the rules followed? But, can we win the war faster? On June 4, 1942, he authorized emergency testing of fully welded Sherman hulls at 3 different production facilities. The authorization came with conditions. Welding had to meet specific quality standards. Welders needed certification. Procedures had to be documented. Inspection protocols had to be established. But underneath the bureaucratic requirements was a revolutionary admission. The Army was willing to change specifications based on evidence from the factory floor. Joseph Moretti found himself pulled from production into a hastily assembled welding development team. Alongside him were welders from Chrysler's Detroit Arsenal, from Pressed Steel Car, from the Lima Locomotive Works in Ohio. Men who'd been working in isolation, making unauthorized improvements, suddenly discovered they'd been part of an unplanned nationwide innovation. The team's mandate was brutal in its simplicity. Develop welding, procedures that could replace riveting completely while maintaining or improving structural integrity. Do it in 60 days. The Army needed production increases immediately. Every week of delay meant tanks that wouldn't reach North Africa, wouldn't support Operation Torch, wouldn't be available when American forces finally went ashore in Europe. The technical challenges were genuine. Welding armor plate wasn't like welding ship hulls or structural steel. Tank armor was hardened steel with high carbon content, specifically heat-treated for ballistic resistance. Welding introduced intense localized heat that could alter the metallurgical properties of the armor, potentially creating brittle zones that would shatter under impact. The team worked 18-hour days in a converted warehouse at the Detroit Arsenal. They tested dozens of welding rod compositions, searching for alloys that would bond hardened steel without compromising armor properties. They experimented with preheating techniques that reduced thermal shock. They developed post-weld heat treatment procedures that restored uniform hardness across the welded joint. The breakthrough came from an observation that Joseph Moretti made during a late-night test session in early July. He noticed that rapid cooling after welding created the most problematic zones of brittleness. Slower cooling produced better results, but slowing the entire hull's cooling was impractical in a production environment. The solution was elegant. Weld in sequences that allowed previous welds to cool gradually while new ones were being executed. The heat from new welds helped temper previous ones, creating a self-regulating thermal cycle. This was the illegal torch trick that would later become legendary. Moretti modified his torch with a custom tip that allowed precise control of heat distribution. Instead of concentrating maximum heat on a single point, the modified torch spread thermal energy across a wider zone. This reduced peak temperatures, while maintaining sufficient heat for solid bonding. The modification violated safety regulations because it altered certified equipment, but it worked. By late July 1942, the development team had created a complete welding specification for Sherman tank hulls. The document was 300 pages long, covering everything from rod composition to welding sequence to inspection criteria. On August 1st, Army Ordnance issued Technical Manual 9-8-15, authorizing welded construction for medium tank hulls. The transformation of American tank production began immediately, but it wasn't the smooth, orderly process that official histories would later suggest. Converting an entire industry from riveting to welding while maintaining production meant training thousands of workers, installing new equipment, and redesigning workflow patterns across dozens of factories. Fisher Body's Grand Blanc plant became the test case. In August 1942, plant management committed to converting one complete assembly line to welded construction while keeping existing lines running. The conversion took 42 days and nearly failed multiple times. Welding equipment shortages forced creative improvisation. The Lincoln Electric Company, the primary manufacturer of arc welding machines, was already running at maximum capacity, supplying shipyards. Tank plants had to wait months for new equipment. The solution came from unexpected quarters. Automotive tool and die shops across Michigan owned welding equipment that sat idle as their normal business had dried up. Fisher Body's purchasing department located and leased more than 200 welding machines from small shops within a 100-mile radius. Training was equally challenging. Riveting required skill, but it was a skill that could be taught in days. Welding required a practiced hand, an intuitive feel for metal temperature and puddle control that took weeks to develop. The Army assigned welding instructors from the Navy yards, men who'd trained shipyard workers. But the volume of workers needing training overwhelmed the available instructors. Fisher Body developed an apprenticeship system. Experienced welders like Moretti each took 3 trainees. Those trainees, once certified, each took 3 more. The training cascaded through the workforce, multiplying expertise geometrically rather than linearly. Quality control became critical. A poor rivet was visible. A poor weld could look perfect on the surface while hiding internal voids or incomplete fusion. The Army instituted X-ray inspection of critical welds, using portable fluoroscopy equipment originally developed for medical use. Each hull received detailed examination before turret installation. Welds that failed inspection were cut out and redone, a costly process but essential for maintaining confidence in the new methods. The first fully welded Sherman hull rolled off Fisher Body's converted line on September 18, 1942. It completed final assembly on September 23. Total production time from raw steel to finished hull, 87 hours. The previous riveted hull average had been 162 hours. The time savings was 46%. 46% faster meant effectively doubling production capacity without building new factories. But the real revolution was just beginning, because once the basic welding techniques were proven, engineers began reimagining hull design itself. Riveting had imposed constraints on tank architecture. Plates had to overlap for rivet placement. Joints had to be accessible from both sides for driving rivets. Complex curves were difficult because forming overlapping plates into curves was nearly impossible. Welding eliminated these constraints. In October 1942, a joint team from Fisher Body and Army Ordnance began redesigning the Sherman hull to optimize for welded construction. They eliminated the overlapping joints, creating butt welds that saved weight. They simplified the lower hull geometry, reducing the number of separate plates from 17 to 11. They introduced compound curves that improved ballistic deflection while simplifying manufacturing. The redesigned hull, designated M4A1, entered production in November 1942. The M4A1 took 64 hours to complete, less than 40% of the time required for the original riveted design. And the weight savings from eliminating overlapping plates and 2,000 rivets meant the hull was actually 600 pounds lighter while maintaining equivalent armor protection. That weight savings allowed the Army to add thicker frontal armor without exceeding the suspension's load capacity, directly improving crew survivability. By December 1942, 6 months after Colonel Fowler's authorization for welding tests, American industry was producing 850 Sherman tanks per month. That figure would climb to 1,000 per month by March 1943. Peak production reached 1,500 Shermans per month in March 1944. Over the course of the war, American factories manufactured 49,000 Sherman tanks. The Soviet Union produced 55,034 tanks, but required a manufacturing base spread across dozens of facilities, evacuated deep into the Urals. Germany manufactured approximately 25,000 Panzer IV tanks, their closest equivalent to the Sherman, using their entire industrial capacity. The comparison reveals the arithmetic of industrial warfare. Germany built arguably superior individual tanks. The Panther and Tiger were more heavily armed and better armored than the Sherman, but Panthers required 300,000 man-hours to manufacture. Tigers took even longer. Shermans required 64 hours of hull construction plus additional time for final assembly, totaling approximately 120 hours. From raw materials to completed vehicle, German tank factories produced quality. American tank factories produced quantity. In total war, quantity had a quality all its own. The welding revolution spread beyond tanks. By mid-1943, welded construction was standard for American armored cars, tank destroyers, and self-propelled artillery. The M10 tank destroyer, essentially a Sherman hull with an open-top turret, went from concept to production in 7 months, largely because engineers could design around welded construction from the beginning. The M18 Hellcat, the fastest armored fighting vehicle of World War II, used welded aluminum armor that would have been impossible with riveting. Its 76mm gun could defeat any German tank, and its 55-mile-per-hour top speed meant it could choose when to engage. The Hellcat's effectiveness in the European campaign owed everything to welding technology that allowed lightweight, high-speed armor design. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The impact extended to Allied production as well. British tank factories, traditionally wedded to riveting, sent observers to American plants in late 1942. What they saw convinced the Ministry of Supply to authorize welding for the Churchill infantry tank and the Cromwell cruiser tank. British production rates increased 40% within 6 months of adopting American welding techniques. Canadian factories building Ram and Grizzly tanks converted to welding in early 1943. By mid-war, virtually every Allied armoured vehicle used welded construction. The Axis powers lagged behind. German tanks used a combination of welding and interlocking plates, but their welding procedures remained more time-intensive. German metallurgy was excellent, but their production methods never achieved the efficiency of American mass manufacturing. Japan's tank industry remained almost entirely riveted throughout the war. Japanese armor was lighter and less capable than American designs, and Japanese production totaled only about 5,000 medium tanks during the entire conflict. The Japanese military never prioritized armored warfare, a strategic decision that proved catastrophic when facing American tank battalions in the Philippines and Okinawa. The human cost of faster tank production is impossible to calculate precisely, but the strategic implications are clear. Operation Torch, the Allied invasion of North Africa in November 1942, landed with substantial American armor support. The tank battles across Tunisia in early 1943 saw American M4 Shermans facing German Panzer IIIs and IVs in numbers that surprised German commanders. General Erwin Rommel's Afrika Korps expected American industrial production to ramp up slowly. Instead, they faced immediate armor superiority. By the time of Operation Husky, the invasion of Sicily in July 1943, American tank battalions were equipped with newer welded hull Shermans that performed reliably in the brutal Mediterranean summer. The invasion of Italy that followed saw American armor operating across mountain terrain where reliability mattered as much as firepower. Welded hulls proved more resistant to stress fractures than riveted designs when tanks navigated rough ground. The Normandy invasion on June 6, 1944, brought the full weight of American armor production to Europe. Approximately 2,000 American tanks landed in the first month after D-Day. Within 3 months, that number exceeded 10,000. The Battle of the Bulge in December 1944 saw the Germans achieve tactical surprise and initial success, but American armor reserves, fed by continuous production, contained and then crushed the German offensive. The Ardennes battle consumed hundreds of American tanks, but replacement vehicles arrived within weeks. German losses couldn't be replaced. German factories were producing perhaps 100 tanks per month by late 1944, operating under constant Allied bombing. The arithmetic was merciless. Every German tank destroyed was effectively irreplaceable. Every American tank destroyed was replaced by 5 more. German tank crews fought with skill and determination, but they were drowning in American steel. The final battles in Germany during April and May 1945 saw American armored divisions racing across terrain that had been impassable to armies just years before. The mobility and reliability of American armor, enabled by efficient production methods, allowed offensive operations at speeds that German forces couldn't counter. Joseph Moretti worked at Fisher Body until the war ended in August 1945. He returned to civilian life without fanfare or recognition, beyond a supervisor's commendation letter and a war bond. He never received a medal, never testified before Congress, never saw his name in the technical manuals that documented the welding procedures he'd helped develop. The engineering establishment absorbed his insights, codified them in military specifications, and taught them to new generations of welders without mentioning the man who'd first recognized that welding could replace riveting if done correctly. For decades, welding textbooks taught the techniques without acknowledging they'd emerged from unauthorized shop floor innovation rather than laboratory research. Yet Moretti's legacy permeates modern manufacturing in ways that reach far beyond military vehicles. Every welded structure built today, from automobiles to aircraft to pressure vessels, follows procedures descended directly from the wartime tank welding revolution. The American Welding Society's structural code, first comprehensively revised in 1946, incorporated the lessons learned from Sherman production. Those standards became the foundation for post-war industrial construction. The automotive industry transformed most dramatically. In 1941, American automobiles were primarily bolted and riveted assemblies. Body panels attached to frames with mechanical fasteners, structural members joined with rivets. The methods were direct descendants of horse-drawn carriage construction, updated with steel but fundamentally unchanged in concept. By 1950, welded unibody construction was becoming standard. The Nash Ambassador, introduced in 1949, featured a welded body structure that eliminated the separate frame entirely. The body panels and structural members formed a single integrated unit, lighter and stronger than traditional construction. The welding techniques came directly from tank manufacturing. Engineers who'd worked on Sherman production during the war brought that expertise to civilian automotive design. The transformation accelerated through the 1950s and 60s. By 1960, virtually every American automobile used extensive welding in body construction. The efficiency gains were remarkable. A 1940 automobile body required approximately 80 hours of labor to assemble. A 1960 unibody structure took less than 20 hours, despite being more complex and structurally superior. The production speed increase directly paralleled what welding had achieved in tank manufacturing. Aircraft construction followed a similar trajectory, though at different timescales. Military aircraft had used welding in structural components since the 1930s, but primarily for steel tube frames in fuselages. Aluminum aircraft, which dominated by World War II, relied on riveting because welding aluminum alloys was technically challenging. Aluminum welding required inert gas shielding to prevent oxidation, a technique that wasn't fully developed until the late 1940s. The Korean War spurred development of aluminum welding for aircraft. The F-86 Sabre jet fighter, introduced in 1949, used welded aluminum fuel tanks that were lighter and more resistant to combat damage than riveted tanks. By the Vietnam era, welded construction was standard for military aircraft fuel systems, structural reinforcements, and secondary structures. Modern commercial aircraft, like the Boeing 787, use advanced friction. Stir welding, a solid-state process that joins aluminum without melting it, eliminating many of the problems that made aluminum welding difficult in earlier decades. The 787's fuselage barrel sections are joined with friction stir welds that are stronger than the surrounding material. The technique traces its conceptual lineage back to the problem that Joseph Moretti and his colleagues solved. How do you join hardened materials without degrading their properties? The pipeline industry learned the same lessons, often through costly failures. The Trans-Alaska Pipeline, constructed in the 1970s, required welding procedures that could handle extreme conditions. 800 miles of 48-inch diameter pipe carrying hot oil through Arctic temperatures created thermal stresses that would destroy improperly welded joints. Engineers studied wartime tank welding procedures, particularly the heat management techniques that prevented brittle zones in hardened steel. The pipeline's welding specifications explicitly referenced military standards developed during World War II. Modern pipeline construction worldwide uses automated welding procedures that maintain precise control over heat input, cooling rates, and weld sequencing. The Trans-Alaska Pipeline has operated for nearly 50 years without catastrophic weld failures, testament to understanding thermal metallurgy in welding, knowledge purchased with wartime urgency and codified in specifications that still govern critical welding today. Pressure vessel construction for power plants, chemical facilities, and industrial processes represents perhaps the most demanding application of welding technology. A pressure vessel failure can release explosive forces or toxic materials with catastrophic consequences. The American Society of Mechanical Engineers Boiler and Pressure Vessel Code, which governs such construction, underwent major revisions in 1950 based directly on wartime welding research. Modern nuclear reactor pressure vessels, containing some of the most extreme conditions humans have ever created, use welding procedures whose theoretical foundations were established during Sherman tank production. The massive steel shells surrounding reactor cores cannot tolerate any defects. Welding sequences are computer-modeled to predict and control residual stresses. Post-weld heat treatment eliminates stress concentrations. Inspection includes ultrasonic testing, radiography, and magnetic particle examination. Every procedure traces back to lessons learned when the Army needed tanks faster than traditional methods could deliver. The offshore oil industry learned through tragedy. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, was traced partially to fatigue cracks propagating from improperly welded bracings. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection. Each disaster prompted investigations that rediscovered principles tank production had proven 40 years earlier. Modern offshore platform standards now require stress relief heat treatment for all critical welds, qualification testing for welding procedures, and continuous inspection during construction. These requirements directly descend from wartime manufacturing quality control. Bridge construction absorbed the lessons more slowly and sometimes tragically. The Point Pleasant Bridge collapse in West Virginia in December 1967 killed 46 people when the suspension bridge suddenly failed during rush-hour traffic. Investigation revealed that welded connections, executed without proper stress management, had developed fatigue cracks over years of service. The disaster prompted nationwide re-evaluation of welded bridge construction. Modern bridge codes require welding procedures that manage residual stress, specify inspection intervals for critical joints, and mandate fracture-critical design where single-member failures can't cause collapse. The Golden Gate Bridge seismic retrofit, completed in the 1990s, added thousands of tons of welded steel reinforcement to protect the iconic structure from earthquake damage. Engineers used computer modeling to optimize welding sequences that minimized residual stress while maintaining production schedules. The sophisticated analysis was fundamentally an elaboration of what Joseph Moretti had done intuitively in 1942, understanding that how you weld matters as much as what you weld. Shipbuilding, where welding first proved itself in large-scale construction, continued evolving. Modern naval vessels are entirely welded, assembled from enormous prefabricated sections that are joined in final assembly. The USS Gerald R. Ford, the newest American aircraft carrier, uses welded construction throughout its 1,100-foot length. The carrier's hull and flight deck represent over 60,000 tons of welded steel, assembled in sections and joined with procedures that trace their lineage to Liberty ships and the welding revolution they sparked. Commercial shipbuilding adopted similar methods. Container ships, the massive vessels carrying global trade, are assembled from welded sections built in highly automated facilities. A modern ultra-large container ship might be 1,200 feet long, carrying 20,000 containers, with every structural member welded. The vessels are assembled in months rather than years, because welding allows efficient modular construction. Sections built simultaneously in different parts of the shipyard come together in final assembly with precision that would have amazed 1942 tank builders, but using principles they would instantly recognize. The economic impact of faster production methods defies simple calculation. In purely military terms, American tank production during World War II cost approximately $7.5 billion, roughly $135 billion in current dollars. That investment produced 49,000 Sherman tanks plus thousands of other armored vehicles. German tank production cost approximately equivalent amounts but produced half the output. The efficiency difference, largely attributable to manufacturing methods, translated directly to military capability. In the broader industrial economy, welding technology contributed to post-war prosperity in ways that are invisible precisely because they became so fundamental. Modern construction, transportation, energy production, and manufacturing all depend on welded structures. The buildings, bridges, vehicles, and infrastructure of modern civilization rest on joints created by processes whose efficiency was proven when America needed tanks faster than traditional methods could deliver. The lesson extends beyond technical specifications. It speaks to fundamental questions about innovation and institutional learning. How do organizations balance adherence to proven standards against the need for improvement? How do they create environments where frontline workers can contribute insights that specialists might miss? How do they respond when established procedures prove inadequate to new challenges? The initial rejection of Moretti's welding proposals wasn't unreasonable. The engineers who defended riveting were applying legitimate caution. Changing specifications during wartime production carried real risks. A major failure could have set production back months. The conservative choice, maintaining proven methods, made sense from a risk management perspective. What changed was the crisis becoming severe enough that maintaining inadequate methods became riskier than trying improvements. Colonel Fowler's decision to authorize welding tests represented institutional courage. He was risking his career on data that contradicted established practice. If welded tanks had failed catastrophically in combat, the decision would have destroyed him professionally. The fact that his bet paid off doesn't diminish the courage it required. The partnership between engineers and skilled workers represented an ideal that American industry often proclaimed but rarely achieved. Engineers brought theoretical knowledge, testing capabilities, and authority to change specifications. Workers brought practical experience, intimate knowledge of production processes, and creative insights into solving real-world problems. Neither group could have achieved the breakthrough alone. The multiplication of improvements throughout tank plants showed how cultural change can exceed individual innovations. Welding was the foundation, but dozens of other improvements built on that foundation. Better welding equipment, improved rod compositions, optimized joint designs, enhanced inspection methods, more efficient plant layouts, all emerged once the basic commitment to welding was established. The cultural shift from "this is how we've always done it" to "how can we do this better" proved more valuable than any single technical advance. The rejected idea became accepted not through brilliant persuasion, but through demonstrated results. Moretti couldn't convince engineers with arguments, but test data from Aberdeen Proving Ground provided evidence they couldn't dismiss. The principle has broad application. Innovation often faces resistance not because ideas are poorly conceived, but because they challenge established assumptions and carry implementation risks. Breaking through that resistance requires either crisis sufficient to force experimentation or evidence compelling enough to overcome institutional caution. The suggestion box at Fisher Body, where Moretti initially submitted his ideas, represented something profound about organizational learning. Every worker possesses knowledge developed through unique experience. The question is whether organizations create mechanisms for that knowledge to reach decision-makers and influence policies. Suggestion boxes, worker quality circles, frontline feedback systems, these aren't just morale-building exercises. They're competitive advantages for organizations willing to take them seriously. December 1942. When welded Sherman production reached full capacity, marked a turning point in understanding how modern organizations could leverage distributed intelligence. The 850 tanks produced that month represented more than manufacturing output. They were testament to what became achievable when institutional humility met practical wisdom, when theoretical knowledge partnered with hands-on experience, when crisis created urgency to question established methods. Those tanks carried American soldiers across North Africa's deserts, through Sicily's mountains, onto Normandy's beaches, across France's hedgerows, into Germany's industrial heartland. Each tank represented not just steel and mechanical components, but accumulated human insight, the recognition that better methods existed, the courage to try them despite risks, the willingness to learn from unexpected sources. The arithmetic of victory can be calculated many ways: strategic planning, tactical brilliance, code breaking, scientific advances, all contributed, but perhaps nowhere were the equations more straightforward than in industrial production. More tanks arriving faster than enemies could destroy them, built by workers who understood their contributions mattered, constructed with methods that valued efficiency as much as tradition, delivered through a production system that could identify problems, implement solutions, and continuously improve at a pace that overwhelmed opponents. Joseph Moretti died in 1978 in Flint, Michigan. His obituary mentioned that he'd worked in wartime defense plants. It didn't mention that his unauthorized torch modification helped build 8,000 tanks in 6 months, or that his welding techniques influenced every welded structure built afterward. But his legacy lives in every welded joint in modern civilization. Every automobile frame, every pipeline crossing harsh terrain, every pressure vessel containing dangerous forces, every bridge spanning rivers, every building rising above city streets. The training pipeline that produced these elite submarine crews represented a transformation in how the Navy approached personnel selection and development. Before Pearl Harbor, submarine service was considered a specialized career path that attracted a particular type of officer and enlisted man. Submarine School in New London, Connecticut, accepted only volunteers who met rigorous physical and psychological standards. The peacetime submarine force was small, exclusive, and operated under the assumption that quality mattered more than quantity. The war shattered those assumptions. Between December 1941 and August 1945, the submarine force expanded from 65 boats to nearly 300. Manning those submarines required training more than 30,000 officers and enlisted men, a tenfold increase in personnel. The challenge wasn't simply teaching technical skills. It was maintaining the culture of innovation and aggressive tactics while absorbing thousands of new crew members who'd never been to sea. The solution emerged through a combination of formal training and operational mentorship. New crew members attended submarine school for basic qualification, learning the technical fundamentals of submarine operations, torpedo mechanics, damage control, and emergency procedures. But the real education happened aboard operational submarines during their rest periods between patrols. Experienced crews would take new sailors through repeated drills, not just the official procedures but the unofficial techniques that had proven effective in combat. The competitive culture within the submarine force drove continuous improvement. When word circulated that one crew had achieved a 3-minute reload time, other crews would drill until they matched or exceeded it. Commanding officers would compare their boat's performance informally, creating pressure for excellence that supplemented official performance metrics. The Navy encouraged this competition, recognizing that the drive for individual distinction produced fleet-wide improvement. This culture of competitive excellence created an environment where innovation flourished. When a crew discovered a better way to position spare torpedoes or a more efficient sequence for hydraulic operations, that knowledge spread rapidly through informal networks. Submarine tenders, the support vessels that serviced submarines between patrols, became information exchanges, where crews shared techniques and compared results. The cumulative effect was continuous evolution of tactics and procedures, driven by frontline experience rather than top-down directive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.